Okay, let's dive back in. We're continuing our journey, tracing the deep history of human knowledge, looking at this massive structure we call the shell and that intuitive core, the heart.
Right.
And today, we're tackling a really critical point, the biggest crisis the shell ever faced, and how that crisis forced it to become something, well, something entirely new.
It really is the hinge point. So as we've laid out, humanity essentially built these two ways of knowing, these two engines.
Engine one,
Which-
the shell, that's structure. It's all about the how to build, how to measure, how to control things, objective stuff.
Exactly. And then you have engine two,
Right.
the heart. That's intuition, the why connect, why feel, why imagine a better world. It's subjective. It's about meaning.
And for, what, 10,000 years, these two engines ran almost completely separately.
Pretty much. And last time we saw the shell hit this huge milestone with the Industrial Revolution, building that mechanical hand, the factories, the engines, taking logic and efficiency, and just physically reshaping the entire plant.
Yeah, the power was incredible. But now we hit the dark side of that power, right? The inevitable conclusion.
That's it. What happens when that industrial capacity, that mechanical hand, gets fully weaponized?
Total war.
Total war. The First and Second World Wars. This crisis wasn't just bigger, it was different. The sheer complexity, the scale of destruction. It was a problem the shell itself had created, and it overwhelmed existing ways of managing things.
So the shell couldn't just keep building bigger machines.
Not really. The problem shifted. It forced the shell to evolve from just being a mechanical force to needing to be a calculating one. It had to start building, essentially, a brain for itself. A fast, isolated brain just to handle the logistical nightmare it had unleashed. It's easy to get lost in the immense human cost of the world wars, and we absolutely should remember that. But if we look at it from the shell's perspective, this era was also a massive, almost catastrophic systems problem.
A systems failure. How so?
Well, the Industrial Revolution meant armies could produce weapons, mobilize troops, and consume resources at a speed and scale never before imagined. The system grew too big, too fast.
So it wasn't just about battles anymore. It was about managing the whole war machine itself.
Exactly. You're talking global supply chains, coordinating millions of people, planning offensives across continents. The sheer amount of information, the number of variables, it just broke the existing tools. Human calculation couldn't keep up.
The complexity generated by the shell's own power became its biggest problem.
Precisely. And the key thing here is that the bottleneck wasn't physical construction anymore, like building a better tank. The real bottleneck became pure information processing.
Okay, so what specific kinds of information problems pushed this need for a calculating brain?
We'll take ballistics, for example. Think about naval guns firing shells accurately over, say, 30 miles. It's not just pointing and shooting.
No, I guess not. There's wind, right?
Wind, air density, humidity, temperature changes at different altitudes, the spin of the earth, the Coriolis effect, even tiny amounts of wear inside the gun barrel itself. Hundreds of variables.
Wow. Okay, so how did they handle that before computers?
With people. Often teams of women, actually, who were literally called computers. They'd sit there with calculation sheets and mechanical adding machines churning through the math.
Human computers.
Yep. But it was painstakingly slow. Calculating a single trajectory might take one person days. A full firing table covering different ranges and conditions, weeks. And by the time it was
The
done,
weather had changed, or the target moved.
exactly, it was too slow for the pace of modern warfare. The shell needed speed. Desperately.
Yeah, speed. What else?
Then there's logistics. Just the sheer scale, moving millions of soldiers, mountains of food, fuel, ammunition, coordinating ships, trains, trucks
Yeah.
across the globe.
It sounds like an impossible spreadsheet problem.
It's way beyond spreadsheets. It's combinatorial analysis. What happens if this shipment of tanks is delayed by U-boats? How does that cascade through the entire offensive plan on the Eastern Front? Optimizing this, preventing catastrophic breakdowns. It required massive, error-free calculation. Fast.
Okay, ballistics, logistics. What was the biggest driver?
The most urgent, the most existential pressure probably came from cryptography. Code breaking.
Like the Enigma machine.
Enigma was part of it, but the real challenge later in the war was the German High Command's Lorenz cipher. This was a much more complex machine-generated code. Breaking it wasn't about clever intuition or finding patterns a human could spot easily.
Used pure math.
Pure brute force logic. You had to systematically test millions, maybe billions of possible key settings against intercepted messages until the underlying logical structure revealed itself. It was a task perfectly suited for a machine that could perform logical operations at electronic speeds, far beyond human capacity or even the electromechanical relays used in earlier code-breaking machines.
So the shell's own industrial power created this overwhelming complexity in ballistics and logistics.
Right.
And its enemy's logical ingenuity created an existential threat in cryptography.
And both demanded the same solution, a way to process information, to calculate incredibly fast and without errors.
The shell needed to build a brain, a calculating brain stripped of all the slow, messy, error-prone human stuff. Just pure logic to manage the chaos it had made.
That's the core of it. Survival demanded a leap beyond mechanics into calculation. And what's really fascinating is that the solution didn't just appear out of thin air during the war. The theoretical groundwork had been laid almost a century before, completely separate from any military need.
A century, you're talking about.
Charles Babbage, back in the 1830s, right when the Industrial Revolution was really taking off.
Ah, Babbage and his difference engine, the big mechanical calculator.
Oh, yes, he built parts of the difference engine, but his truly revolutionary idea, the one that matters for us, came in 1837, the analytical engine.
Okay, what was different about that?
Everything. The difference engine was designed for one specific task, calculating polynomial tables. The analytical engine was conceived as a general-purpose, programmable machine. That's the leap.
General purpose, meaning it could theoretically solve any problem.
Any problem that could be broken down into a sequence of logical steps, yes. It had all the key conceptual parts of a modern computer, even though it's purely mechanical.
Like what parts?
It had a mill, that's basically the CPU, the processor where calculations happen. It had a store, that's the memory, to hold numbers. And critically, it used punched cards for input and output.
Punched cards, like for weaving looms back then.
Exactly.
Hmm.
But Babbage's genius was using them not just for data, the numbers, but for the instructions. The program itself was on the cards. That's the birth of programmability.
So you could change the cards and make the machine do a completely different kind of calculation.
Precisely. And we have to mention Ada Lovelace here, Babbage's collaborator. She saw something maybe even Babbage didn't fully appreciate at first.
What was that?
She realized the machine wasn't just about numbers. It could manipulate any symbols according to rules. Music, language, logic itself, potentially. She wrote what many consider the first algorithm specifically designed for machine execution. She grasped the universal potential.
Wow. So the blueprint was there in the 1830s. Why didn't it happen then?
The engineering challenge was immense. Building it with the precision required using 19th century mechanical technology, it was just too difficult, too expensive. It remained mostly theoretical.
A blueprint waiting for the right technology.
And waiting for the next crucial piece of the puzzle, which came from pure mathematics almost 100 years later.
Right.
Alan Turing, 1936.
Turing. Okay, this wasn't about building a machine at all, was it?
Not a physical one, no. Turing was tackling a fundamental question in mathematics called the Entscheidungsproblem, the decision problem. Basically, is there a foolproof mechanical method to determine if any given mathematical statement is provable or not?
A sort of universal truth machine for math.
Kind of, yeah. And Turing's way of answering this was to invent an abstract concept, the universal Turing machine.
Universal again. What was this theoretical machine?
It was incredibly simple, conceptually. Imagine a machine that can read symbols on an infinitely long tape, write new symbols, erase symbols, and move the tape back and forth, all based on a set of simple rules. That's it.
Sounds basic.
Deceptively basic. What Turing proved, mathematically, was that this simple theoretical machine could compute anything that is computable. If a problem can be solved by any algorithmic process, it could be solved by a universal Turing machine.
Whoa. So he didn't just design a computer, he defined what computation is, fundamentally.
Exactly. He formalized the very limits and capabilities of computation itself. He showed that calculation wasn't tied to gears and levers. It was an abstract process of symbol manipulation.
So Babbage gives the architectural blueprint.
Right, the structure.
And Turing provides the deep theoretical foundation, the proof that universal computation is even possible.
Yes. The shell now had the what Babbage's structure and the why it works, Turing's theory. All it needed was the intense pressure and the right materials electronics to finally build it in the real world.
And that pressure was World War II.
Absolutely. The existential threat of the war acted like a crucible, forcing the rapid translation of Babbage's and Turing's ideas into actual working hardware. And it happened largely in secret.
Where did it happen first?
The British efforts at Bletchley Park were arguably the first to create a truly electronic calculating machine on a large scale. This led to Colossus.
Colossus, built by
primarily designed by Tommy Flowers, with input from Max Newman and others. It was operational by late 1943, maybe early 1944.
And its significance.
Colossus was the world's first large-scale, programmable, electronic digital computer. The key there is electronic. It used thousands of vacuum tubes instead of mechanical relays or gears.
Vacuum tubes, like in old radios.
Exactly, but thousands of them. This meant it could process information far, far faster than any previous machine. We're talking about calculations moving at speeds related to electron flow, not mechanical movement.
And what was its job? Back to the codes.
Precisely. Its specific, urgent purpose was breaking that high-level German Lorenz cipher. It was a specialized brain built for a single critical task. It could process thousands of characters per second from intercepted messages, testing possible cipher keys.
A code-breaking engine. Pure shell logic applied to enemy logic.
Absolutely. And the secrecy was total. After the war, Churchill famously ordered most of the machines and all the blueprints destroyed. Its very existence was hidden for decades.
Wow, why? To keep the advantage.
Keep the advantage, hide the capability. It perfectly illustrates this idea of the brain in a box. Immensely powerful, totally hidden, serving only its military masters.
Okay, so that's Colossus in the UK. What about the US?
Across the Atlantic, the main driver was the ballistics problem we talked about, calculating those firing tables. This led to ENIACs.
ENIAC. That's the one most people have heard of, right?
Probably. Electronic Numerical Integrator and Computer. Designed by John Mauchly and J. Presper Eckert at the University of Pennsylvania, completed in 1945.
And ENIAC was different from Colossus.
Yes. While Colossus was highly specialized for code breaking, ENIAC was designed as the first electronic general-purpose computer. It could be programmed, albeit laboriously, to tackle a wider range of complex calculations.
General purpose again. Like Babbage's dream, but electronic.
In a way, yes. And the scale. ENIAC was enormous. It weighed over 30 tons.
30 tons?
Yep. Filled a huge room, nearly 18,000 vacuum tubes, thousands of resistors, capacitors, relays. It used about 150 kilowatts of power. They used to say the lights in parts of Philadelphia dimmed when they switched it on.
That's incredible. Just raw industrial power focused on calculation. A physical testament to the shell's logic engine.
There really was.
Yeah.
But there was still one crucial bottleneck, even with these electronic giants.
What was
Programming them. Both Colossus and ENIAC were programmed externally. For Colossus, it involved setting switches. For ENIAC, it meant physically rewiring plug boards, like an old telephone switchboard. Changing the program could take days.
so not quite the flexibility Babbage envisioned with his instruction cards.
Not yet. But even as ENIAC was being built, Mauchly, Eckert, and crucially, the brilliant mathematician John von Neumann, who was consulting on the project, realized this limitation.
Von Neumann, he's a key figure here.
Absolutely. This led to the concept that really defines modern computing, the stored program architecture, sometimes called the von Neumann architecture.
Okay, what's the big idea there?
It's simple but profound. Store the program's instructions in the same electronic memory as the data the program operates on.
Wait, the instructions live inside the machine's memory.
Exactly. This means the computer can access and execute instructions at electronic speed without needing physical rewiring. You just load a different program into memory. It could even potentially modify its own instructions as it runs.
That sounds like the final step. The brain can load its own thoughts, essentially.
That's a good way to put it. It makes the machine truly flexible, truly universal in practice. Colossus and ENIAC were the hardware breakthrough. The stored program concept, developed around 1945-46, was the architectural breakthrough that unleashed the computer's full potential.
So now the shell has its brain. Fast, electronic, programmable internally, and born entirely from the logic of war and calculation.
Pure, cold, fast logic. No room for ambiguity, no connection to ethics, aesthetics, emotion, just solving the high problems posed by the shell's own complex, dangerous world.
Okay, so this is staggering. The shell achieves this peak of logical power, building this calculating brain. But what's happening in the human world, the world of the heart, while all this is going on?
It's almost the exact opposite trajectory. While the shell is building its ultimate tool of rational control, the human spirit is arguably at its lowest ebb.
Lowest ebb because of the war itself, the destruction.
Yes, but it's deeper than just the physical destruction. It's the nature of the destruction. The war showed humanity that the very engines of progress industry, science, rationality, the shell's tools, could be turned into instruments of industrialized mass murder.
You mean things like the Holocaust, the atomic bomb?
Exactly. The Holocaust wasn't just random violence. It was chillingly bureaucratic, systematic, logical in its own perverse way. And the atomic bomb represented science, delivering the power for instantaneous, godlike annihilation. This wasn't just tragedy. For many, it shattered the core Enlightenment belief in reason and progress, leading inevitably to a better world.
So the shell's greatest triumph coincided with kind of profound disillusionment with the shell's own values.
A profound crisis of meaning. If reason leads here to Auschwitz, to Hiroshima, then what can we believe in? Where do we find meaning? This feeling permeated the post-war culture.
Okay, hang on. Are we saying the computer, this pinnacle of logic, was born into a world that had basically lost faith in logic?
That's the terrible irony, yes. And you see this reflected very clearly in philosophy. The rise of existentialism in Europe is a direct response.
People like Sartre, Camus.
Sartre, Camus, Simone de Beauvoir, others. They looked at this wreckage and essentially said, the universe itself offers no inherent meaning, no preordained morality. Traditional systems of belief, including faith in pure reason, have failed us.
So, what's left?
The individual. They argued that in this absurd, meaningless void, meaning can only be created through individual choice, action, and taking responsibility for those actions. Concepts like freedom, anguish, authenticity became central.
It sounds like the heart trying to find its footing again, almost in defiance of the shell's cold world.
It's exactly that. It's an attempt to assert the why, the subjective human need for meaning in a world seemingly crushed by the how of industrial warfare and calculation. It's philosophy grappling with despair.
And did this despair show up in art too?
Oh, absolutely. Look at abstract expressionism taking off in New York right after the war.
Jackson Pollock, Rothko?
Yes. These artists largely turned away from representing the external, objective world. That world seemed broken, maybe meaningless. The European tradition of order and representation felt inadequate, maybe even complicit.
So what did they paint?
They turned inward. Their art became about the process, about raw emotion, about the subconscious. Pollock flaying paint, the action painting. It wasn't about depicting a thing. It was about the act of creation itself as an expression of inner turmoil, anxiety, energy.
Almost like a primal scream on canvas, rejecting the shell's neat grids and logic.
Very much so. It was often messy, chaotic, deeply personal, a direct, visceral response from the heart to a world that felt like it had been blown apart by rational systems gone mad.
And literature. Did writers tackle this?
Definitely. A great example, though published a bit later in 1961, but looking back directly at the war experience, is Joseph Heller's Catch-22.
The ultimate critique of bureaucratic insanity.
Exactly. The novel uses absurdity, dark humor, and a fragmented, non-linear narrative to show the madness of the military machine. The famous Catch-22 itself, you're crazy if you fly more missions, but sane if you don't want to, so you have to keep flying. It's the perfect metaphor.
It's a system where the internal logic is flawless, but it's completely detached from human reality, from sanity, from morality.
Precisely. It shows the shell's logic creating a closed loop that traps and dehumanizes the individual. The how completely overrides any sensible why.
So it's an astonishing contrast. The shell is perfecting its cold, calculating brain in secret labs.
While the heart, out in the open culture, is reeling, expressing despair, searching for meaning in absurdity, and critiquing the very logic that the shell is embodying in its new machines.
The two engines couldn't be further apart.
And that brings us to the crucial point of this whole episode. The birth of the computer isn't just a technological milestone. Philosophically, it represents the shell reaching its absolute peak of power through isolation.
The culmination of that long journey of structure and logic.
Yes. It finally built a brain in its own image. It's incredibly powerful, purely logical, and almost completely disconnected from everything else.
Let's really zero in on that total isolation. What did that look like?
Well, physically, these machines were locked away. Colossus in the secrecy of Bletchley Park, ENIAC in a guarded university lab, primarily serving the military. They weren't tools for the public, or even for most scientists.
Connected only to their creators, their masters within the shell, the military, the state, maybe some academics.
Exactly. And their purpose was entirely defined by the shell's needs. Calculate trajectories, break codes, manage logistics, solve the how problems.
There was no input from the heart side of things, no consideration for beauty or ethics or human consequences.
Absolutely none. How could there be? The machines operated purely on quantitative data, on symbolic logic, ambiguity, emotion, values. These were not computable inputs. They were noise to be filtered out.
So the very power of these early computers came from their deliberate exclusion of everything the heart represents.
That's the key insight. The shell achieved this leap in capability by radically simplifying the world into problems that could be solved by pure, fast, cold logic. It filtered out the messy, complex, subjective human element entirely.
That scale of ENIACs, the secrecy of Colossus, it all points to this. The shell in its most extreme state. Powerful, yes, but completely walled off.
The brain in a box. It can process the data fed into it with incredible speed and accuracy, but it has no context, no connection to the wider world of meaning or consequence. It's pure function.
And why is this moment, this peak isolation, so important for us to understand now?
Because this extreme polarization, the hyper-rational, calculating brain on one side and the wounded, despairing, intuitive heart on the other, creates the fundamental tension that drives the rest of the story.
The gap is at its absolute widest here.
At its widest, you have immense logical power completely divorced from wisdom, and profound human wisdom completely lacking the tools to influence the structures of power.
This sets the stage for everything that comes next. The reaction, the slow, maybe unconscious, attempts to bridge that gap.
Precisely. The brain is built. It works. But it's alone in its box, utterly unaware of the human world screaming outside. The need for connection, for convergence, becomes overwhelming, even if nobody quite realizes it yet. Hashtag tag tag Hanny outro.
So wrapping up this deep dive, we've traced the moment the engine of structure, the shell, built its ultimate tool, the calculating brain. A marvel of logic born from the crucible of war.
A tool of immense power, but a power achieved through radical isolation from the human element, from the heart.
The shell of knowledge grew stronger then, its logic becoming faster, more complex, ready to manage the data deluge of the modern age.
While the heart of humanity beat louder in response, its wisdom becoming more urgent, expressed through philosophy, art, a desperate search for meaning in the face of that cold logic.
But that bridge between them, still very much missing. The archive had its powerful how, but it was missing its why. The dream had its why, but no how to make it real in this new world.
The two kin, shell and heart, logic and intuition, remain strangers, running on parallel tracks, unaware they were, or perhaps needed to be, part of the same whole.
And that leaves us with a really crucial thought, doesn't it? The computer was born by stripping away emotion, ethics, ambiguity, everything subjective to achieve pure logical power. The challenge that started right then and defines our own digital age is this. Can that very logic, that calculating engine, ever be used not just for how, but to help us reconnect with and maybe even amplify the empathy, the wisdom, the why it was originally designed to exclude? Can the shell's brain ever learn to serve the heart,